All right, so we've looked at this problem. You looked at this over your homework now. So we're going to dive more in today about first order and second order reactions. So we looked at finding rate laws. Rate equals K times the concentration of reactants raised a certain power. You know that the power is the exponent is the order. And then so what we're going to look now is we're going to learn and dive in a little bit more about what does it mean for a reaction to be first order? What does it mean for a reaction to be second order? What are some other things that we can learn from that? And so you see the slide here says first order reaction. We're going to look at what we call integrated rate laws. If you're familiar with calculus, we're going to integrate some formulas. If you don't know calculus, don't worry. We don't have to know calculus to be able to know what we need to know for the exam. So we look at these different types of reactions, right? You could have a reactant. It could turn into one thing, two different things, or three different things. So they're just giving you different examples of possible scenarios. And then we look at our rate. Remember, rate is the change in concentration over the change in time. So delta is change. So change in concentration of A over change in time, the interval that we're looking at. And then negative because A is a reactant here. So we're losing the reactant. We can also look at the rate in terms of the rate law. Rate equals K times the concentration of A. Now, because this is a first order process, we see that the exponent is 1. So overall, this reaction is a first order process. So everything we're going to talk about here is going to relate back to first order processes. And it's going to help you, based off given different data, help you identify if it's a first order process or not. So when we look at a first order process, we can use calculus, and so we can take the rate law, which let me go back, right? We can take this rate law, rate equals K times the concentration of A. We can take that rate law and we can integrate it, and if we take the integral, we get this formula here. And when we get this formula, looking at a couple of the variables here, so ln is natural log. We have K still, right? We have our K value. And then an integral, remember, we want to integrate over a certain time interval. So in this case, it's from time 0, which is the time you start at, to a certain time t. Whether that's 1 minute, 2 minutes, 4 minutes, 8 minutes, a year, 5 days, whatever that time interval is going to be. So A naught is where we're starting, the concentration that we start at, and this is the concentration we're ending at. And then T right here is just related back to this T. What time interval are we looking over? Again, that would be given to you in the problem. Now, we can rearrange this formula, and we can put it into the form y equals mx plus b, which you should be familiar with. That is the equation for a line. And so when this is kind of the important thing here, we'll look at a graph on the next page. Right, this is your y-intercept. Slope is K. That's important to make note of. When we graph this line, the slope will be our K value, negative, but it will still be the K value, so we can find K. And then B would be the natural log of your starting concentration of A. So again, this right here is what's important to make note of. If a reaction is first order, a plot of, so if we were to graph the natural log of A versus T, the concentration of A, it would give us a straight line, and that straight line, it would have a negative slope, so it would be sloping downwards, and it would look something like this. So this is obviously not ln, but we'll look at this process. They're measuring pressure versus time. It's okay, we've been measuring concentration, but we can also look at it related to pressure. Remember, the pressure of a gas is directly related to how much of the gas you have. The more of the gas you have, the greater the pressure is going to be. So when we look here, the greater amount of gas we have, the higher the concentration is. So there's a direct relationship between pressure and concentration. So that's why we can kind of use them interchangeably when graphing data. Now, we notice that this is not a straight line. You see a curve to this line. So when we look at kinetics and when we look at these graphs, we're going to be looking for where are we getting the straight line? And then what's the axis of our graph? Well, this is just pressure versus time. It's not natural log. So it's not a straight line, but if I were to take this data and I were to do the natural log of the pressure versus time, what you see here is the straight line. When that happens, when we have the natural log versus time and it's a straight line with a negative slope, They might try to trick you and give you a straight line with a positive slope, but that's not what we're looking for. We're looking for a straight line with a negative slope. Negative slope goes back to this negative right here. So when we have that straight line with a negative slope, we know it's first order. And so from this graph, what can I learn? Well, these are the things that we know. First thing we know, it's first order. Second thing we know, we can find the k. You could find the slope of this line, y2 minus y1 over x2 minus x1, or like rise over run, right? We find the slope, and then whatever the slope is going to be negative. We just turn it to a positive value, so your k values are always positive. But if we take the negative of the slope, we get our k value. That's another important thing to take from this. And then we know the y-intercept, wherever it crosses the y-intercept, we know that that would be the natural log of our initial concentration. So again, make sure we're knowing natural log relates back to first order processes. Now, if we were to graph this as a curved line and we were to get this graph and it's also a curved line, then it's not first order. We don't know what it is. When we look at these graphs, we're going to be looking for a graph of a straight line. Don't worry about this. It's from an old textbook. We don't need to worry about that. And so that's first order. Now let's look at second order processes. So instead of having Ka with a 1 exponent, now we're going with a 2 exponent because it's a second order process. That's the only difference here. So what would we look at? We're not going to be looking at natural log. What we're going to be looking at is the inverse. So the graphs that we're going to be concerned with do I have a natural log graph? Do I have the inverse of the concentration versus time graph? Or do I have just the normal concentration versus time graph? Again, you see here, this is in the form y equals mx plus b. This formula right here is on your periodic table. They give it to you, so you just need to know how and when to use it. Same thing, let me back up for a second. Same thing for this formula here. It's on your periodic table. So again, don't memorize it. You just have to know how and when to use it. So if we were to graph this line, we're looking for a straight line, but the thing to notice here is the slope is not negative, the slope is positive. And so this line will be a straight line, but it'll be going up, it'll have a positive slope. And we'll look at a graph of that here in a second. But if you were to have the inverse of the concentration versus time, and it gave you a straight line, these are the three things we would know. We would know it's a second order process. If you find the slope of that line, that's your k value. And then you know your y-intercept would be not the natural log, but the inverse of the initial concentration. And so see, if we take a different reaction, they give you the data here. If you look at the natural log versus time graph, it's a curved line. Also, this has a negative slope, which is not what we're looking for. But if we were to take these values and instead of the natural log, we take the inverse, as you see here, we see that's a straight line with a positive slope. You could then do rise over run, find the slope of that line, and that would give you your k value. But again, the important thing to note here is that we know it's second order. Why is it second order? Because we have the inverse of the concentration versus time graph giving us the straight line. So a big thing with these integrated rate laws, and you'll see practice questions later this week where you're going to be given different graphs, and based off the graphs they give you, you have to identify the order of the reaction. And again, you're paying attention to the axes and which one's giving you the straight line that you're looking for. When it comes to half-life, so half-life is defined as the time required for half of the reaction to react. And so if I start with 100 at pressure of 150, how long does it take to get to 75, which is half of that? How long does it take to get to 37.5, which is half of 75? That's the half-life. And when we look at half-life, you're given a formula for half-life for first-order processes on your periodic table. And so this is going to get into deriving the formula. We're not really going to worry about that just due to time. So you can flip through this if you want to see how they derived it. You can look at it. But this is what I would tell you to focus in on. This is given to you on your periodic table. And I would make a note that this is the half-life for a first-order process. So if you're given a graph, you know it's a first order process, you then know the formula to solve for the half-life, or how long does it take for half of your reactant to go away, or not go away, but to be reacted. The main thing to note here, and this is going to be the main difference between first order and second order, is the half-life is only dependent upon your K value. And this is the note. I would write this down. I'd make note of this. It does not depend on the initial concentration. It doesn't matter how much you start with. First order process is the only thing that factors into the half-life is your K value. What is your K value? So if I were to give you a problem, say what's the half-life, if you know the K value, you plug it in here and you can solve for how long it would take for half of your reactant to react. Make a note of that. It's on your periodic table. That's for first order processes. And so you can practice this. You can use that formula. You can try to solve that. There's your answer right there. If you can't get that answer, then go on to office hours later and you can ask and I can show you how to do that. Second order process half-life, again, they're deriving the formula. Don't worry about it. What I would tell you to focus on is this formula right here. Notice the difference. It's 1 over K, but also now we're multiplying by your starting concentration. So the important difference between first and second order processes deals with half-life. Second order processes, it does depend on the starting concentration. First order does not. Second order does, and we can see that in the formula. They don't give you this formula on your periodic table. I would tell you this is definitely a formula you need to memorize. If they ask you to solve for the half-life for a second order process and you don't know the formula, there's no way you're going to be able to solve for it. So make sure you know the difference between the formulas and understand that first order processes, when we go back here, first order processes only dependent upon K. Second order processes, half-life is dependent upon not only K, but your starting concentration. And here's practice you can do. If you want to pause, you can work this out, and then you see your answer right there. And if you can't get the answer, then just let me know, come in the office hours, and we can work through it. One thing we see here, K is temperature dependent. So as temperature increases, so does the rate. So as your temperature goes up, the rate goes faster. Which, again, why do we speed things up? We're giving them more energy. As you give the reactants more energy, they're moving faster. As they're moving faster, they're colliding more often. As they collide more often, the reaction occurs faster. So understand K is temperature dependent. And so as the temperature goes up, the rate of our reaction will go up, and that just means K is changing. All right, we'll stop there for today, and then we'll pick up with this collision theory later this week.